Good afternoon, everyone. Thanks for joining me after the lunch break. My name is David Smith, and I'm the Chief Community Officer at Revolution Analytics. And today, I'd like to talk to you about the open source R language, and particularly how you can implement big data analytics in real time with the R language. Now, before I begin, I am contractually obliged to remind you that you need to silence your cell phones, or I'm told a huge laser will come and smite thee should your phones go off. Not my problem if that happens, blame the organizers. But first I want to introduce myself a little bit, and also the company I work for, which is Revolution Analytics. As I said, I'm the Chief Community Officer at Revolution Analytics, which means that I'm responsible for supporting the open source R community and the solutions that we provide, including technical support for the open source R language. And in fact, for almost 7 years now, we've been the leading provider of software and services to people who are using R to implement advanced analytics. We do that in the traditional way, in much the same way that Red Hat supports Linux in the commercial environment, the same way that Cloudera supports Hadoop in the commercial environment. We support R being used for business applications. One of the ways that we do that is with our own enhanced distribution of R. We bundle up R itself with some proprietary technology, which I'll give some hints at later on in the presentation, to create a big data, a big analytics software platform based upon the language R, which we call Revolution R Enterprise. It's really exciting for me to be working for an open source software company in this era of pretty rapid change, especially given the big data revolution, which was really driven by open source technologies like Hadoop and NoSQL databases. To see some recognition of the influence of open source through the Gartner Magic Quadrant for Advanced Analytics, which was released just a couple of months ago. If you take a look at that report, which includes the traditional sort of legacy software vendors for doing advanced analytics, but right up there in the top right-hand corner of Gartner's Magic Quadrant is 3 open source software companies who are really sort of delivering a revolution in what people can do with advanced analytics with big data. And very proud, of course, that Revolution Analytics was one of those 3. I mentioned earlier on that I've been with Revolution Analytics pretty much ever since it started. They brought me on because I'm a data scientist, and I've been working with the R language and data analysis in R for quite a long time. And in fact, I'm the co-author of the Introduction to R manual that actually comes with R when you download it off of the web. And can I just say, by the way, how cool it is to be able to say data scientist? This is a term that I actually really like. And one of the reasons is, not just because the data science revolution has become so strategic for companies who are looking to implement predictive analytics with big data, but the main reason why we like data scientists as a term is because I used to call myself a statistician. And in fact, that's what I did my degree in, was statistics back at the University of Adelaide. But then I'd find that I'd go to cocktail parties like that reception last night, and somebody would come and ask me, what do you do? And I'd say, I'm a statistician. And suddenly they would grip their wine glass very tightly and back slowly away, as if my boring rays were going to destroy them at any moment. But data scientists are cool, right? This is awesome. Being able to talk about real applications of data that are really changing the way that business is operating, and data scientists have really become rock stars. And I'd really like to thank, the likes of Nate Silver, who predicted the last election and appeared on just about every news channel imaginable. I'd like to thank the likes of Hillary Mason, formerly of Bitly, who did so much for popularizing data science, and especially women in data science, and not to mention appeared in Glamour magazine. And also the likes of all those data scientists out there that have been developing the community, such as Hadley Wickham, a very prominent data scientist in the R community, who's developed a lot of the data visualization technology that exists in R, and we'll see that where that appears out in the real world a little bit later on. So I want to tell you a story about how data science impacts us on a day-to-day basis. And I'd like to start with a very personal story. This is a website. I was browsing around the web a couple of years ago, actually just last year, doing research. Actually, I was looking at Bad Astronomy, one of my favorite blogs, and something popped up on that which was kind of surprising to me. An ad appeared, and that part's not surprising, but it was an ad that I was actually interested in. I had been sort of shopping around for a while. I'd heard about this cool new Lytra camera a little bit, and suddenly this ad popped up. It was telling me about this thing that I particularly was interested in. I didn't think anybody else was interested in. And right there was on this blog that I read regularly, and I clicked through and I checked it out. And it's actually a really cool camera if anybody wants to check it out. They just came out with a new one. It's very awesome. But kind of what I want to go into in this talk is how did we go from me, random person, browsing the web to an ad appearing on my screen that was really perfectly tuned to my interests? And we can answer that, first of all, by having a look at some of the clues that an advertiser might have which would lead them to perhaps believe that I might be interested in this particular type of camera. We can start with a few things. Well, first of all, I'm on an astronomy website. So astronomy, lots of photography in astronomy, geeky kind of stuff. So that's a fairly good clue that a brand new type of camera might be interesting to me. But there are lots of other clues here as well. First of all, you notice that I'm using Chrome on a Mac. At one point, that would have been fairly techy rather. These days, not so much. But perhaps another signal there, for those of you that have ever used Flash Blocker in Chrome, very cool add-in. Advertisers actually pick on that fact that I'm trying to block ads by blocking Flash, but that in itself is a signal that I'm a type of techie person that might be interested in an ad not delivered through Flash that I may well be interested in. So little clues there that can be picked up on, but probably the most significant clue that comes into this is my own personal profile. I'm logged in to my personal profile in Chrome, that little icon you can see in the top right-hand corner. But most importantly, this particular website is connecting into social networks, Facebook and Twitter and so forth. And if I've ever liked that page or tweeted from that page, the advertiser may be able to get direct information from those social networks about my interests, my friend connections, my history on the web. More likely, though, the advertiser has purchased demographic information about millions upon millions of people, including me, that they figured out how to translate back into a record in a database about thousands of millions of people to this particular person visiting this particular website at this particular time, and one of the variables is interested in photography, and that led that particular ad to be chosen. But there's a lot of moving pieces in this particular puzzle. So how did that actually come to be? Well, it's a combination of several things. And just trying to use this mouse, here we go. One of these is going to make it go forward. There we go. If you want to grab the buzzword bingo card out of your file folders, this is a really good part of the talk because you'll get a good advancement to winning the trip to Hawaii. Just kidding, there is no actual buzzword bingo card. But this is happening in real time. Right there, as that web page was rendering, it recognized who I was, picked an ad that was appropriate to me, and popped it up there on the screen. I'm going to give up on the mouse. It's dealing with big data. There's not a whole lot of data about me personally that is perhaps related to this particular ad being picked at this particular time. But I am one of millions upon tens of millions upon particularly hundreds of millions of people that could have been visiting that website at that time and had to choose between all the information about those potential candidates in order to choose between possibly thousands, maybe even hundreds of thousands of ads that may be displayed at that time point, which are all simultaneously being bid upon by all the potential advertisers to show something to me at that point in time. And it's using predictive analytics. Now that is the technique that combines together all of that data in real time with a predictive model to actually choose for this particular person at that particular time, what is the ad that I can display that that person is most likely to click on and interact with and hopefully generate a purchase at the end of the day. So let's talk about each of those elements in turn. And I'd like to start with big data. Big data is a much maligned phrase. It is a buzzword today. As somebody mentioned in the talk I was in earlier on, we know it's a buzzword because we always capitalize it when we write it down. I thought that was kind of cool. But big data is also quite misunderstood. And the analogy that I like to use for big data is crude oil. Crude oil sitting there under the ground. Crude oil is big, there's lots of it. It's quite inaccessible. It's messy. It's contaminated with lots of pollutants that need to be filtered out and dealt with before we can do anything with it. It's expensive to deal with. It's difficult to store. It's difficult to transfer. All of these properties carry over to big data as well. But something that also the big data has in common with crude oil is that with enough refinement, with enough processing, with enough attention and care and money, you can actually get something very valuable out of big data once you distill it down and process it and use it in downstream processes, like, for example, your car's engine. The other piece of the puzzle, in addition to the big data that led to that ad being presented to me in real time, is a predictive analytics model. And I want to spend a little bit of time, for those of you that might not be familiar with the background of predictive analytics, to how this was done. What we start off is what I'm going to call here factors. This is information that we know ahead of time. And it's information not just from one person in this particular case, but from thousands, millions, hundreds of millions of people collected in some kind of data collection effort. Now, in these kinds of consumer applications, the kind of data we might want to collect at the outset when trying to build a predictive analytic model is things like user IDs as we observe people browsing around the web, and the browsers that they use, and the time and the date that they visit various locations across the web. We might want to tie that sort of interactive information in with demographic information that there are dozens of data providers that are willing to sell you these days. Things like, for those people that we know were visiting or browsing the web at those times, what purchases have they made in the last month, 2 months, 6 months, a year, whatever. From social networks, we can find out information about what friends they have and what they have purchased, which may give some influence into some insight rather, into the types of products that I might be interested in. But collectively, to build a predictive model, we start with information that we know and we can collect and we can measure. And that's our starting point. Ultimately, what we want to do is make some kind of prediction. That's why it's called a predictive model. What is the ad that I'm most likely to click in? What is the product I'm most likely to buy? What is the price point at which I'm most likely to buy that product? In terminologically, I like to say we generate scores from these predictive models, but what do scores mean? It's those things that we're trying to predict from the data that we already know. Product of most interest, offer of most likely sale. On Google, what Google does is every time you search, there's a predictive model that knows from your history that Google knows a lot about you, what is the web page that you're most likely to click on from that search query. And that's sort of the algorithm behind Google's entire search business. In financial services or in products management, you might want to forecast for a commodity type product. What's it going to sell at this point in time, a week down the line, a month down the line? And this is how Wall Street makes all of their money in the commodities business. Same thing for ad networks as it is for house prices. What is the optimal bid at which somebody is actually going to win an auction for some kind of dynamic market? All of these things can be predicted using predictive models, just given enough data that we know and a predictive model to go from that data to one of these scores. So ultimately we want to go from data we know to a prediction or a selection or a recommendation, the thing we want to get out of the predictive model, and we need some way to connect those two things together. What we want to do is create scoring rules. Scoring rules is just a simple set of mathematical transformations. Could be just a couple of lines of code if you write it into C or Visual Basic that transforms all those factors that we know in real time into the actual prediction or selection that we want to use to generate which ad appears on the screen, for example. And what this talk is about is how you actually generate those scoring rules. And this is what statistical software does. This is what advanced analytics software does. There are lots of tools out there on the market that can do that. My personal favorite, as you might have guessed, is the R programming language. I like R a lot because it's free, it's accessible, it's got an amazing community of people working with it, but most importantly in this particular context is because it does literally everything in terms of predictive models. There are dozens, probably hundreds of just different classifications of predictive models that you might want to use. There are decision trees, logistic regression, neural networks, k-means clustering, ensemble models. There are hundreds. And the nice thing about R is because it's the actual language that researchers use to develop these models in the first place. Somebody doesn't just like publish a paper about a new ensemble method, they also publish R code as free code that you can download. And so what that means is for whatever type of predictive technique you want to use, it's already right there in R. So that's a really cool thing. But ultimately, whatever particular technique you use, what you are doing is starting with a data set, all that known information you have, using a predictive model to generate a set of scoring rules, and then those scoring rules will be used in real time to generate the prediction, the selection, the recommendation that's actually being used in the operational system in real time. Come back to some of these details in a moment. In the meantime, I just want to take a little digression and introduce you to R, just with show of hands. Who knows somebody in their organization that's using R today? So that's about 70% of people. And if you could leave your hand up, who's actually using R themselves at the moment? Probably about 25%. And that's a pretty standard type of ratio. I do a lot of work with organizations that do predictive analytics in their operational businesses. And I find in most places, at least 75%, someone in that organization is using R, but most people there don't know about it. And one of the reasons for that is because R has been around for a long, long time. In fact, it was first developed in the mid-90s by a couple of professors out of New Zealand called Rossa Harker and Robert Gentleman. But for a lot of that time, it was confined within the statistics community. Everybody who did a statistics degree used R in their coursework, they'd used it in their research, they used it in their publishing. But until data science came around and data science became popular and strategic, it wasn't really well known outside of the academic community. But that's not true today. Today, R is easily the most widely used data analysis, statistics, data science software in the world. And we estimate that it's used by more than 2 million data scientists. And that's very easily an underestimate. I mean, just to give you one very specific example, a course that Coursera ran last year on data science, so predictive models with statistics, predictive models with R, quite an advanced course that had 365,000 registrants for one course alone. So there's so much interest in people using R. One of the reasons, once again, is that it is the most powerful statistical programming language available. It's not just that everything is already there, but it's a flexible language. We had a great talk earlier on from Erica, who talked about sort of using R for doing basic statistics, t-tests, and so forth. She mentioned that there is no function in there for doing a population standard deviation, which is true. But one of the nice things about R is you can very easily extend it and add your own functions to it with just a very small amount of code. And that's what all these researchers in the community have been doing over the last 10 years or so, is extending R by writing their own functions in what we call packages. One of my passions is data visualization, and R is just amazing at doing static data visualizations, at least. It doesn't do interactive stuff, point and click, transformation, but if you want to create a really beautiful picture of data on paper or on the web, there's sort of nothing like R to do that. In fact, if you look at the New York Times, a lot of the very cool data visualizations that they do are developed in the R language. And in particular, there's a new feature in the Times, just came out last week at Upworthy. They have a Senate forecast based on a predictive model of historical polls and results in elections, which is itself developed in R, and there's some great visualizations in that as well. Twitter uses R for all their internal development, and their blog has some great examples, a great map of Twitter users around the world. And speaking of maps, this is actually a picture that Facebook included in their IPO documents. It's a visualization of every single friendship relationship in Facebook in late 2012. This is literally billions of relationship. There are hundreds of millions of Facebook users. Each of those have hundreds of friends. When you have a look at those relationships and plot them on a map like this, you just see some really cool things. Like, for example, you can see the population centers, obviously, and the fact that Facebook is not well penetrated into Brazil. There's all sorts of insight that you can draw just from a simple, well, this isn't simple, but a powerful data visualization like this. And these are things that R is very strong at. If you're interested in data visualization, a blog that I recommend is the Flowing Data blog, which often features graphics done in R and tutorials for how you can do them yourself in R. As I mentioned earlier on, R is open source, and one of the things that is great about that is R is free. You can download it and use it at any time. But actually, I think the most important thing about R being open source is the open source community that is built around it. There are millions of users, but there are actually hundreds of thousands of developers of R who contribute every day with new functionality, new capabilities. And if you're starting off on a data analysis problem and you're thinking about using R in a particular segment, for example, in volatility forecasting in commodities in the financial sector, you can do a search like that, volatility forecasting in commodities in R, and find that somebody has done most of what you're probably trying to do already, publishes as a package or as a workbook, and you can actually get started very, very quickly that way. The last point I want to mention about R is, especially with data science becoming so strategic, many organizations are actively trying to hire data scientists to make sense of all the data that they've collected in their big data strategies. And there definitely is an imbalance between supply and demand for data scientists. Data scientists are difficult to find, and they do charge a pretty penny for their services. But for those organizations that have adopted R as their platform for data scientists, they do have it a little bit easier because there is a constant supply of new data scientists coming out of the academic community that are already trained in the R language. Because as I mentioned earlier on, anybody who studies statistics or data science does it using R. So, and that it's not just R as well. I mean, these young graduates are also typically trained in modern data platforms like Hadoop, NoSQL, and so forth, which are often part of the solutions that are built around R as well. So that's a brief intro. If you'd like to know more about the history of R and some of its applications in industry, there's a white paper available, and you can see the link on your screen right there. Just a few quick stats, by the way, on the growth of R, because it has been exploding in the last few years. You can see on the chart on the left, this comes from the Rexa data mining survey, which has been done every year or so for the last 7 or 8 years. And you can see those trends. The number of data miners, this particular survey is focused on data miners, the report using R has been growing steadily over the years, and it's now up to 70% of all data miners. And in fact, data miners, as with all data analysts, use a variety of tools, but the number who use R as their primary tool in exclusivity has also grown rapidly over time. Talking about talent again, one of the reasons why it's expensive to hire data scientists is that in the recent Dice.com salary survey, R was actually ranked amongst all IT skills as the highest paid skill there. So if you're thinking about getting into learning R, that might be a motivating factor. In a recent O'Reilly survey of data scientists, it's the most used data science language, with the exception of SQL, data processing language, which everybody has to use, of course. RedMonk ranks it as the number 15 of all programming languages. This is based on an analysis of usage, based on GitHub commits to projects using these languages, and Stack Overflow questions of these languages. And that's of all languages, Java, PHP, C++, R ranks number 15. And it's growing faster than any other data science language out there. So R is definitely something to get into. Just a quick plug, I mean, that's what we do at Revolution Analytics, is to bundle R into a product we call Revolution R Enterprise. Probably the only downside to R, which was mentioned in a talk a couple of minutes ago, is that it is an in-memory application. It's designed for research, it's designed for quick prototyping, quick access to data, but being an in-memory application means you are limited in the size of data that you can process with the R language. What we do at Revolution Analytics is bundle R with proprietary packages, add-ons that we create to make it work with big data. So you can use R for high-performance, scalable analytics with big data. We also port it to enterprise platforms, enterprise databases, Hadoop, operating systems that IT typically uses. So it's portable across all those enterprise platforms. And we design it in such a way that it's easy to integrate R into business workflows. So if you want R as the engine behind the operating system that actually selects which ads appear on a website, you can do these real-time analytics with some of our integration tools. So what it includes is everything you get in open source R. We don't modify R, we just recompile it for performance and then include it with our additional tools that provide big data scalability, high performance analytics. We provide development tools for programmers, data scientists that are working in the R language to have an integrated development environment where they can set up workflows and do debugging and share with their colleagues and then deploy those into operational systems. We improve the types of data you can connect to with R, so collecting into existing databases or existing file formats, and provide the multi-platform architecture and the support and training and services that go along with that. So with that plug behind me, I want to sort of go back to our original example of developing a web application that in real time selects an ad to display to me based on predictive analytics. And if you're thinking about sort of building an application like that, any kind of real-time environment that's deploying analytics, it's a complicated process, but I can break it down into 5 sort of very broad phases. Number 1 would be data distillation, figuring out what data you have in your own environments or is available from outside the building, perhaps with data vendors or data streams or social data that could perhaps speak to the problem. Secondly, working with a data science team to work with that data to develop a model that predicts or recommends what you need for your system and validates that model both with the existing data that you already have and with real-time systems to make sure it works in a production environment. Once that model is done, is actually deploying it out into the real-time system. But you're not done that, not done at that point. Once a model is actually live, there is a continual process to make sure that that model continues to work. This is a part that I think a lot of people might overlook in some situations, but as with all models, these are living, breathing things, and the environment around them changes all the time. There's been a good example recently with Google flu trends. You might remember a couple of years ago, Google was being lauded for being able to predict the rates of flu simply based on the rate at which people were searching for flu-related terms in the Google search engine. That famously broke down quite terribly in the most recent flu season. And one of the reasons for that is because that model had not been updated since it had been first deployed by the Google team. So it is very important to be able to continually monitor the performance of your models and update them through number 5, model refresh, when that's necessary. You can either make that a regular process, refresh 6 monthly, weekly, sometimes even daily, and then deploy those new models into your systems. So let's have a look at each of those steps in turn. First one is data distillation, and I'll do this sort of in the context of unstructured data such as you might find in Hadoop. So you start off with this data lake, this sort of data warehouse with all sorts of data in it. You know, it might be traditional structured data as you might find in a relational database, but it might be unstructured data, log files, it might be real-time data like census streams. It might be textual data that you want to do semantic analysis or feature extraction on. All of that data can go into a big data environment. And I think this is one of Hadoop's real strengths. And this ability to just bring in all sorts of data from different environments, data that previously you may have simply thrown away because it was too expensive to collect in a traditional enterprise data warehouse, and bring that into the Hadoop ecosystem. But data in Hadoop is not readily accessible to data scientists for analysis. It's very difficult to do extractions. We have some tools that can help with that process. One of them is an open source library called RMR, which is used by data scientists in the R language to process data that's sitting directly in Hadoop. But one of the outcomes of that in this process of building a predictive model is to generate structured data, in some kind of local data warehouse. Now I've sort of glossed over a lot of details of how you can go from unstructured data like language and log files into structured data, but again, these are some of the things that the R language is really, really good at. And to give you just one example, I was working with a client that was doing some social prediction based on tweets that were sent to their particular handle, and just being able to stream in from the fire hose, all these tweets into a Hadoop environment, plus other demographic variables. There's a function that already exists in R that can go from a piece of text to a sentiment score, based on positive words like, negative words hate. You can actually rank the sentiment of a tweet from -1 to +1. R, there's a package in R that already does that, and using a technique like RMR, you can actually apply that R function across all the tweets in the Hadoop database, and then generate just one column of data. For each tweet, it's sentiment, -1 to +1. And you can do all those same kinds of things with other types of textual and unstructured data as well. Just to give you one example, the particular sort of client I was thinking about there was an airline. They were analyzing the tweets that went to @United and @Virgin US and @Delta. Doing this over time, measuring sentiments. But when they actually compared the sentiment scores, they got out of this analysis with the US consumer rankings of the airlines, is almost exactly the same. But the consumer rankings only come out once a year, whereas now in real time, they can detect changes in sentiment that might be related to real-time factors in their operation. So that's the data distillation phase. Step 2, the model development cycle. This is where you need to get data scientists involved. I am a data scientist, so I'm biased on this front, but I think there is a lot that data scientists bring to this process of understanding where data comes from, working with somebody on the business side who understands what the problem is that the organization is trying to solve, and then working with the IT people and those with the computer science expertise to make that data accessible and do that processing. But the data science cycle starts with looking at the data we've extracted, figuring out what variables, what features in the data are going to speak to the prediction, the selection that we want to make, perhaps doing some sampling from that data. Now, sampling sounds like anathema, in this big data environment, but in fact, sampling is a very powerful technique that data scientists can use to prototype and develop models. Sometimes it's aggregation. We have data that's measured on the minute-by-minute basis, but really the type of trends we're looking for are more on the daily or the weekly basis. Aggregating things down into more manageable amounts doesn't just save time, it can actually produce much more powerful models at the end of the day. Then there's variable transformations. A lot of sort of people look at machine learning, for example, as a promise to say, hey, I can just take my big table, I can feed it into a machine learning algorithm, and magic happens. But there's a big step you've missed there, which is actually transforming the distribution of those variables, converting things like states into regions, all that kind of messy but important data processing that data scientists use needs to happen with the data store before you go into the actual modeling process. And a data scientist will typically try dozens of different types of modeling techniques, try and find which ones predict well. And sometimes prediction isn't even the only criterion that we're looking at. We're also looking at models that have low failure rates. Now, if you're looking at, for example, a medical example where you're building a predictive model to try and identify a disease, the number of times it gets the disease correctly predicted is important, but so is the number of times it gives a false diagnosis. And these, again, are the types of things that data scientists work with. Then there's the model refinement process. Once we've set it on the data we want to use, the actual modeling technique we're going to use, then actually going back to the original data stores, working with new data and comparing it to historical events. We saw that in the keynote this morning, that very cool feature where you could go backwards on that time series prediction and see if we had predicted in the past, how did it actually compare with the predictions we actually got. And data scientists use that routinely to validate their models and refine them. And then, again, as I said earlier on, once that model is actually in production, there's a continual process of benchmarking that model and making sure it's conforming to reality, because reality keeps on changing. The output of all that process, now that I've gone down sort of one level of detail, is to generate that predictive model that we're going to use in the real-time system. It's relatively small amounts of information at this point. and you're going down from terabytes, maybe tens of terabytes of data that came from the big data lake, the oil refinery. Once you've boiled it all down and built that predictive model, you might just end up with 3 or 4 lines of code that actually goes into the production system. So we're kind of divorced from big data at that point. But as we go through this cycle, in whatever system you use, but as of course I recommend the R language, the data scientists are still working with that big data to actually try and build the most powerful predictive model that's going to be deployed into that system. One thing to remember about this is a cycle. Data scientists will go through this process. It can take weeks, it can take months sometimes if you're doing a really big process. But every time the data scientist needs to actually go back to the data, time comes in here because you've got to load the data out of the system, and then you have to fit the predictive model. And if that predictive model takes 8 hours to run, and I've definitely seen that in many, many situations, the practical consequence of that is a data scientist can only tweak that model once a day. And this is why it can take months to do. You don't just do one and done, you actually have a look at lots of different options. So anything that we can do to cut down the time it takes to go around that cycle means that data scientists can produce much more powerful models. And this is one of those areas where open source R, in the big data context, does have some challenges. The blue line that you see there is the performance of one particular function in R. It's GLM. That's the function that you use for doing generalized linear models, like logistic regressions, for example. The x-axis is the size of data, so up from 50,000 rows up to 5 million rows. And the y-axis there is the amount of time it takes to process a model of that size. So in the blue line, you can see just R increases very rapidly as the data sets get not even particularly large, just hundreds of thousands of rows, up to about 80 seconds. And then at that point, actually on this particular environment, R crashes. It says just not enough memory available to do it. One of the things that we do with Revolution or Enterprise is add as a package an alternate version of that function, which we call RxGLM. And that does parallel processing out of memory. So you don't ever have to bring all the data into memory at once. And because it's running in parallel, it means it's much, much faster, even for small data. But most importantly, as the data grows and grows and grows, the amount of time it takes for the data scientist to go a loop through that cycle increases linearly. Now this is just going up to 5 million rows. That line extends out as large as the data goes. This particular example was just done on a simple laptop. But you can actually run these same types of models on much bigger environments with more and more CPUs. You don't need more and more RAM, but it's available. But in fact, the way our algorithms work is you can distribute these computations across the nodes on a grid or across the blades in an enterprise data warehouse or across the nodes in a Hadoop cluster. So you can divide and conquer this problem down into little pieces. You start off with the big data there on the left, split it up into lots of different segments. And each of those segments may be, for example, one node on a Hadoop cluster. Each of those segments gets processed in parallel using the algorithm for k-means or logistic regression or whatever to do that statistical model. All those run in parallel and then are combined to generate one master result, as if you'd done all the data at one time. Now, I glossed over one very important bit there when I said combined. It's actually really, really mathematically difficult to combine together the results of many tree models or many clustering models. But that's what our developers up in Seattle do, is create the algorithms that can run parallel and distributed to do these advanced predictive models that exist in R already, but will now work with big data on these computational clusters. So the data scientist has gotten the data. They've gone through that cycle several times. They've developed a predictive model. How do we actually deploy that out into the wild? As I said earlier on, in most situations, the actual code that you need to generate to transform factors into scores is actually relatively small. And so that gives you lots of options of the way you can do that. Some applications, for example, will generate SQL queries that will have as input the factors and as an output the scores, which you can run directly in a database. You can code it up yourself, especially in Wall Street where performance is key. Writing in C++ or Java is often the way to go and deploy that directly into the operational system. You can use the existing R environment, as I'll show you later on. I have some clients that do it using Hadoop. Another good way is to use the PMML framework. Who here is familiar with PMML? Okay, just a couple of people. PMML is actually quite awesome because you can take a predictive model, translate it into a standardized set of XML, as it turns out. And there are lots of PMML engines out there that will run in a database or in an operational system that will do exactly this transformation from factors with the PMML code into scores. There are some limitations, which I'll come to in a minute. There's another very crude way to do it, but this is actually, I find this surprisingly common, and that is simply to do it all ahead of time. If you know in advance all of your customers, you could just run this analysis or this prediction for every single one of your customers, and then when that customer walks in the store, you can just pull out that pre-computed score or prediction from a lookup table. So a lot of people that have their operations based on databases do it this way, just because it's very simple, but it is less real time because it's hard to update those models in a real-time environment. So I want to tell you a little bit of another story now, another application, which was, at least hypothetically, wandering through the store, in the mall, I see a blender right there on the windows, and I say, hey, I need that blender, and I go ahead and buy it. So the question is, and this is something that marketers really want to know, is why did I actually go ahead and buy that blender? Could be for lots of reasons. You know, it might have been just I was bored, I was browsing through the mall and say, hey, cool blender, and got myself a blender. That probably doesn't happen too often, but you'd actually be surprised. It might also be that I saw an ad, or in a TV, or in a magazine, and I reminded myself, hey, you know, last Cinco de Mayo, I burned out my blender. And then when I was walking through the store, I remembered that ad, and they're on a special, so I went and got that. It might have been I was prompted to do so. I got a coupon from Williams-Sonoma to say 50% off blenders, and I went to the mall and went ahead and got one, or I went to Amazon and I bought one. It might have been some special event in my life. I might have just moved, and I got an email through the sort of customer loyalty system that said, hey, you've just moved, you know, go and get some new appliances. That actually happened to me, that particular one. It might just be a particular time in my life. You know, it might be that every anniversary I go to the store and I buy some kind of new thing that way. Lots of sales happen that way. I might have been browsing through a web store and got a particular recommendation, you know, based on my purchase history. Or I might have been browsing a catalog. That seems kind of old school, that, you know, a company might send me a big book of information and I might browse through that. But you would be surprised. Williams-Sonoma, I think in 2012, generated about 25% of their revenue from catalog. You might ask the question, how do they actually figure that out? You know, if I actually get a catalog in the mail and I flick through it, and then 2 weeks later, or maybe 3 weeks later, or maybe a month later, I go to the store and I buy a blender because I saw it in the catalog, how do they actually tease that together? Now that's a really important question for marketers, because all these different channels, you know, whether it's catalog, whether it's email, whether it's TV, whether it's in-store, whether it's promos, you know, all these things cost money. And the big question for a marketer is, am I spending the right money in all these different channels, and how effective is it? And this is actually a question that with big data and predictive models, you can actually answer. One of our customers is DataSong. They're a marketing analytics company. And what they do is they work with big retailers like Williams-Sonoma and help them answer this question. So they start off with the data that the retailer provides. So starting with the bottom there, they can get access to the retailer's customer database. They can get access to the retailer's marketing history, so their interactions with DoubleClick and other online providers. They can get information about their email campaigns. They get information about their catalog campaigns. Then they can combine all that information with purchase data from the likes of Axiom and Experian and Omniture to create a big data warehouse. And that's where the data scientists come in. The data scientists look at all the data in there, combine that with individual transactions. And if you look at just one person, you know, you can see over time, you know, January, I got an email. February, the catalog landed on my desk. March, I visited the web store several times because I was looking for something. Then in April, I got a promo, an email, and then in June, I went ahead and bought a blender. Now, just looking at that sequence of events for one person doesn't give you a whole lot of information. It's very hard to tie my purchase of the blender to any one thing. But aggregate that information over hundreds of thousands of consumers, and then some patterns emerge. You can see that after a catalog drops, there is a surge of purchases of certain types of products. And with that borrowing strength across all sorts of consumers, they can get very clear pictures about how effective all of these different marketing channels are. And answer that question that marketers have been asking for a long, long time. Half of my marketing spend is wasted, but I don't know which half. And now Williams-Sonoma can figure that out because they can see the actual impact of all the different channels compared to the spend that they make it. And more so, they can actually tie that information back to individuals. Catalogs, for example. Every time I get a catalog, it goes straight from my mailbox into the recycling bin, which sits right next to my mailbox. Great system. But there are other people that like that. They can actually detect of their customer database who is most likely to respond to a catalog and send it just to them and save money by not sending the catalog to everyone else. And as a result, I've noticed I no longer get the Williams-Sonoma catalog in the mail. So how was this actually implemented in practice by DataSong? It started by taking all that data you saw there on the left-hand side and loading it into Hadoop. So all that marketing channel data, those behavioral variables, the promotional data, what they call the overlay data that comes from the individual customer records, goes into the big Hadoop infrastructure. That's where the data scientists start. The data scientists get access to that data in Hadoop through some connections that we provide in Revolution Enterprise. They start off with exploratory data analysis. They have a look at that data visually. They build what are called time-to-event models. So that thing about saying email here, purchase here, that's what time-to-event models are all about. And they use what are called generalized additive models, survival models, to actually implement the predictions from all of those individuals. Then finally they use the variant of the database method. They develop that particular predictive model. They run scores for all their retailers and all their customers and load all that information back into Hadoop, which can then be accessed by the retailers, which then download it for their own operational systems. And this is a lot of data. They rerun those models every single day for all of their customers, so that ultimately in Hadoop they're doing 5 billion scores per day per retailer. Now, Hadoop is not really a real-time system, and as it turns out, this is not a real-time application. What actually happens is that the retailers download the scores and they load that into their operational systems themselves. But if you actually want to implement your own real-time system, there are options. Because ultimately, going back to the website example, all that needs to happen is I'm at a website, they know factors about me, my browser, my person ID, my social network connections, all that information I sort of pointed out in the very first slide. They have a predictive model they've already developed. Perhaps they deployed it with PMML. PMML transforms that information about me into a prediction, which ad to show on the website. And that can all run very, very quickly in real time. The one restriction that I wanted to mention about PMML is that it doesn't work for all types of predictive models. There's a very specific set in the PMML standard that works with PMML. But a lot of people today are using much more advanced predictive models, particularly ensemble models. If you haven't heard of ensemble models, it's basically a way of saying, let's do every possible model type imaginable, decision trees, neural networks, logistic regressions, whatever, mash them all up together. And what happens at the end of the day is you get a much more robust prediction. This, in fact, is how Netflix does their recommendations. The winner of the Netflix challenge a few years ago actually won that competition with an ensemble model of 96 different predictive models. Unfortunately, PMML can't handle that, but there is another way to do that, and that's actually to use the system that you used to build the model in the first place, in this case R. The data scientists use R to actually develop the model, and then in the R language there's just one function, it's just called predict. And predict takes the model you generated and generate the scores from the data that you know. So it's a very easy transformation system. Also for companies that need to deploy changes to these models quickly into real time, it means you don't have to recode into C or Java into something like that. The cloud is a really good environment for doing these real-time scoring systems. Deploy it directly into Amazon, have R sitting there as a listener with the predictive model already deployed, as an object into the R system. The factors become the inputs into the API, outputs are the scores, and that actually is the technology that drives your real-time system. And I would mention that Revolution Enterprise is available in the Amazon Marketplace, so you can actually try this right now if you like. So finally, refreshing the model. Once we've got that model out in practice, it's busy generating its factors, applying the predictive model, generating the scores, but how do we know if it's doing that job well? Well, fortunately, this is happening in real time, so we actually know if I clicked on the ad. We actually know if the customer bought the product, and we can compare the scores our model generated to the actual outcomes that happen in real time, and make that comparison to see if it's doing well. Now, what well means in this context really depends on the actual applications. Like I said, in medical applications, you want to have very few false negatives, and false positives might be okay. But in the advertising situation, if you show the wrong ad to somebody sometime, that isn't a big deal as long as you get the maximal throughput of people actually clicking on those ads. I'm not going to go into all the details of how you might do those comparisons, except to mention this is another area where R is very strong, setting up different ways to compare the performance of models with actual outcomes. You can set yourself a threshold for when that model diverges enough from the actual outcomes. You actually want to go back and redo that and then recalculate the model. But this gets us back again into the big data environment. When we want to actually go back and recalculate the model, we've gone from just those very simple scoring rules into actually needing to go back to a new set of data to redo the model. And if you need to redeploy that model, say overnight, the amount of time it takes to do that is again going to be an issue. And because a lot of companies have their source data in an enterprise data warehouse system or perhaps in Hadoop, it can be prohibitively expensive to go through that extract process again. That distillation from the oil that I talked about earlier on, in some situations that can take more than a day just to do the extract. And if you want to refresh that model on a daily basis, that's clearly going to be a problem. So my recommendation in that environment is to actually do the model rebuilding directly in the data platform itself. This is something that our software Revolution Analytics can do. If you have your data in Hadoop, you can actually take the R code that does the analysis and run that directly on Hadoop itself. You don't have to move the data out, and the Hadoop nodes themselves actually act as the computational nodes, which in turn increases the processing efficiency. So the way that works in the Hadoop environment, whether that be Cloudera or Hortonworks, is that you take the R code that actually implemented that model, you run it directly on the Hadoop platform, and then technically what happens is at each individual Hadoop node, R is doing its computations on its subset of the data. Those results get recombined and recalculated, and then get returned as a new model object, a predictive model, which you then go back and deploy into the real-time environment. The same thing applies if you have the data running in an EDW like Teradata. You can take the same code, load it directly into the Teradata database, and in that case the computations run on the blades in the Teradata environment itself. So to summarize, we talked about big data, we talked about real time. What do those things mean? And the answer is it depends on where you are in the process. When you're first starting with the oil, the data lake, big data is really big. It's commonly petabytes. We're even getting up into the exabytes in some environments. Google has exabytes of data. So there's massive amounts of data that you could potentially work with. And just the extraction process, the selecting, the distillation, that can take a long time, minutes, hours, sometimes even days. I've definitely said that. I've seen that. So that's when people talk about big data, especially in the media, that tends to be what they're referring to as way down at the storage level. But that's typically not the data that we work with when we're actually building predictive models. Once you go through the distillation process, you tend to get down to gigabytes or terabytes of data. There's no less important data, it's actually the important data that you've selected through the distillation process. Then when you build the models on that data, real time in this context means the amount of time it takes for a data scientist to press go to when they actually pick up the results. It could be minutes, it could be hours, it could be overnight. It depends on the particular environment, but the more you can make that number go down, the less time it takes for the data science to process a model, the more times they can go through the cycle, and the more powerful that predictive model will be as a result. Now, when we actually get to the integration layer, when we've deployed the model into a real time, a machine is connecting with another machine to go from the data it knows to the prediction you want to generate. What does big data in real time mean in those environments? Big data is actually probably better measured in a rate of flow rather than absolute size. For one individual, because you're down to the predictive model and just the data about one person, it's a relatively small amount of data. But you have a website that may be serving hundreds of thousands of people simultaneously. So the amount of data your predictive model now deployed needs to deal with might be in the order of megabytes per second. But it needs to respond very, very quickly to handle that load. It needs to come back in milliseconds from here's the data for this person to here's the prediction that I generate. But then when you get down to the actual user, the person that's actually interacting with your model, things change again. For one particular person, the amount of data you're dealing with is pretty small, perhaps kilobytes per second, which is good because often the ways that we interact with predictive models these days are with our smartphones. Google searches, applications, recommendations, web stores. There's not much that data that can go over that 4G connection, but that doesn't matter because all the big data is actually driving the results that come through that relatively small amount. And the response time, we're talking about humans at this point. I press a button, a second or two later, a result comes back. What I don't know, of course, is thousands of other people are doing the same thing at the same time at the millisecond level, but at the user level, we're just talking real time in a human sense. So with that, I wanted to ask the question, how did one particular website figure out what was interesting to me? And the answer was, it was predictive analytics, it was done with big data, and it was done in real time. And that's what's up with that. Thank you. I'll also say that I put together some resources if you want to learn more about R on our website, revolutionanalytics.com/whatisR. And I believe we have some time for some questions. Any questions out there? Oh, a question in the back, yeah? Mm-hmm. Yes. Yeah. Yeah, the question was, is it a common pattern to actually extract data out of Hadoop into, say, a relational database? Actually, it doesn't have to be a relational database. It could be any sort of local data store. Is that a common pattern? The answer is yes, because at that model development phase, you want to get the data close to the data scientists because you want to minimize the time it takes to go around that cycle. And you could leave it on a remote server. You could even leave it in Hadoop. But that means every time the data scientist wants to do another step in that process, they've got to go through that ingestion process. Now, by doing the local data store, you're inherently sort of severing the real-time part of the process. You're taking a snapshot of the data. But a data scientist can actually do really good work just with a snapshot, developing those predictive models. That might take some time, but I think I skipped over it. But part of that process is that they're validating the model is go back to the real-time system and make sure things are still working. So it's really just about the efficiency and the productivity of the data scientist is why I think that's a good idea. That's right, yeah. Once we get to the operational phase, when we're actually deploying these models, the data scientist is kind of out of the picture at that point. So a data scientist is quite happy, at least, for one-time load, let's wait overnight to get the data. But when it's in production and we want to do an automated update, that doesn't fly anymore. So that's a situation where you want to take the data and actually, take the model and load that into the data platform and run it there so you no longer have to move the data around. Very good. Question over there? Yeah. It's actually both. The question was, in terms of solving that sort of big data problem with R, is it splitting up the data or splitting up the algorithm? And the actual answer is both. So we actually, if you take a regression algorithm, for example, for those of you who might have done it at school, it's just a few matrix equations. But that only works when you have all the data together. What we have done is basically restructured those equations to say, if you can only see a small piece of the data at the time, what does it look like? And then because you've got separate sort of equations running, you can actually run them in parallel on different pieces of the data, which improves the performance. No, you run the entire data set, yeah, which is actually really important in many situations to be able to do that. Data scientists can get a picture of how the data moves with samples, but if you're trying to detect very rare events, for example, you need to work with all the data for the final model. Any question at the back of them? I think the question was, do we use GPU processing? And the answer is no. We've actually found for these big data problems, distributing the data across many nodes with CPUs is actually the best way to go. There are also some technical issues we're doing with GPUs, which we can chat about offline if you like. Anything else? All right, thank you everyone for your attention.